Right. Well, good evening, everybody, and welcome to the third lecture in the 2020-2021 Railway Division North Eastern Centre programme. My name is Louise Shaw. I'm the chairman of the North Eastern Centre for 2020-2021. Welcome to everybody from around the world this evening. This is not just a North Eastern Centre audience, but we have people from around the rest of the world with us this evening, which is fantastic, and welcome, especially for those people from far overseas. Got some parish notices to go through, which hopefully will give you a better idea of what's coming up in the next couple of months, not just in the UK, but across the different centres in the UK, I should have said. So I've split the events that are in the centres in October and November, and also a seminar on the 19th of October. All of these events, with the exception of the seminar, are free to join. There are different railway division centres. You can see we've managed mostly to separate out the dates so there are no clashes, and anybody is welcome to go to any one of those individual talks by going to near you and registering with the local centre through whichever means they have chosen to use. Our next event is on the 17th of November, which is about decarbonisation. It's going to be a joint meeting with South Eastern Centre and the IET Yorkshire region. David Shearers will be talking about the judicious mix for traction for decarbonisation. If you go to the Near You webpage, all the registration links will be put on that. So please keep an eye on that page. If there are any changes by way of timing or similar, that's where you'll find out. We've got several means of communicating with you all and you with us, which are up on your screen now. Our Near You webpage is the primary source of information, apart from the paper programme cards, which people should have received now. There's also the Railway Division's own web page where a number of bits of information as well as the events can be found. You can also filter the IMechE's events page specifically for railway events, specifically for free railway events. We have a LinkedIn group if you wish to join through there. We also have a mailing list which Richard Gibbon and Derek Rayner, our joint honorary secretaries, curate, and you can be added to that mailing list by using that email address you see on the screen there. Or if you have any comments about the programme or events, please also feel free to use that email. As a special experiment this evening, we will also have something we've called an after party on Zoom, which you'll be able to access using that very, very long link you can see in front of you. Don't worry, you don't have to write that down. You can copy that and paste it straight into your browser. Alternatively, I will copy and paste it straight into the chat box, which you should be able to make happen on the right-hand side of your screen. And if you scroll through the chat, you should be able to pick up that link at any time this evening. So the purpose of that is to enable people to have more of a face-to-face chat virtually, because the platform we use for these events at the moment doesn't enable that face-to-face chat. It doesn't enable informal communication. Everybody is welcome to stay on to that. We'll go straight there after we've finished this evening's lecture and the Q&A. But don't feel that you have to. That's completely voluntary. So, a little bit of advice before we launch into the lecture about how the mechanics of this is going to work tonight. So we will have our lecture this evening followed by Q&A. You can use the chat box on the right-hand side of the screen to enter your question to be put to our lecturer. You can select whether that question is visible to everybody or just visible to the panelists this evening by clicking in the to box, and then a drop-down menu should appear in which you can select all attendees or all panelists. If you use some kind of pseudonym when you're logging in, please do identify yourself. It makes it much easier for me to run the Q&A and understand who's asking which questions. I'll compile the questions at the end and we'll run through them then. And if you've got any technical issues, you can address that query to all panelists in the chat box, and that will go directly to our HQ support person this evening, Fiona Wong, who is extremely competent and capable and should be able to help to resolve just about anything. So, without further ado, I will introduce tonight's speaker. Fiona, do you want to swap onto Felix's slides? So tonight we're joined for the chairman's address by Professor Felix Schmid. So if you're looking for the Swiss politician of 1454 to 1524, that's completely the wrong Felix Schmid. Felix was born in Switzerland and studied electrical and electronic engineering at Zurich before moving to the UK to join GEC in 1978. He moved to Birmingham in 2005 from the University of Sheffield, where he built up the original Railway Systems MSc engineering course over a period of 11 years. Prior to that, he was a control systems engineering lecturer at Derailment University for 10 years. Since his retirement earlier this year, he's been appointed as Professor Emeritus of Railway Systems Engineering at the Birmingham Centre for Railway Research and Education. Felix is a huge enthusiast for all things railway and all things engineering, and amongst other things is a regular judge, as am I, at the Railway Challenge, which happens each year, apart from this one, in June at Stapleford in Leicestershire. Tonight's lecture is one of the most prestigious in our calendar, if not the most prestigious. It's entitled The Long History and Exciting Future of Railway Systems Thinking. Over to you, Felix.
Thank you, Louise. Is the sound okay?
Lovely.
Okay. But I can't move the slides at the moment. That seems to be, oh. As Louise has already mentioned, I'm retired from the University of Birmingham, but I still do a reasonable amount of teaching and collaborating with the university. The picture is from Rail Live about 3 years ago, where I was asked to give a talk in the guise of George Stephenson. Now, some people think it was George Stephenson impersonating me. That is completely wrong. My personal interests are in systems thinking, railway traction systems and railway control, and you'll hear about that a bit later, and also very much into ergonomics and people in systems. I will be talking about railways as complicated and complex systems and what I call a systems approach to railways. What I want you to do by the end of this lecture is to be happy that we need to change. I want you to think about the value of people, and I want to highlight the value of education, which will be in the sort of latter part of the talk when I talk a little bit about my career. So first of all, an apology. This is an educational lecture. It's not just a fun lecture. I'm sorry about that. I'm going to talk about systems and how the railway fits in, and then I'm going to give a history lesson, which hopefully some of you will not have all heard before. I'm going to talk about systems of systems and what are emerging properties when you put things together. Then I'm going to talk about the determinants of complexity and complication in railways, which elements are particularly complicated and which are particularly complex and difficult to manage. I'm going to touch on Perrow's normal accident theory, and then I'm going to sort of give a little bit of a sideline on trying to prevent failure is not a sound strategy. You may be puzzled by that, but we'll see. And then I'm going to talk about the V system life cycle and the complex system adaptive cycle before, as I said, going on to my background. So you can read this probably faster than I can tell. So a system is basically an entity in an environment, is influenced by the environment, and it influences the environment. And we do that all the time. It may have just a single purpose, but many systems have got multiple purposes. And it's really lots of bits making up something which the individual bit can't do on its own. So a system will have a boundary, which will be physical and temporal or just notional. And a system can also be a set of principles or procedures to make something work, something to do something. It's an organized scheme or a method. And of course, the railway has the purpose of transporting people and goods. There are, of course, other purposes as well. Some of them are probably employment of people. Some of them are support of government initiatives. So railways have been around for much longer than is sort of generally seen. And what I consider sort of the forerunner of modern railways appeared in German mines in the 1600s. The thing which you see on the right is, of course, a modern imitation of a Hund, which was the German word dog for small carts for mines. And basically they had two planks and a slot in between, a guide pin which made sure that the dog stayed in the right place, and the boards in order to give smooth running, which of course allowed you to carry more load with an animal or a child or an adult pushing or pulling the load underground. The guidance meant that your tunnels could be much smaller because, of course, you only want to build big tunnels where you have got something to extract, not just for access. So this was the first form of smooth running surface and guidance in about 1600. German miners brought this technology to the Lake District, and that's where we sort of saw the start of it. The early railways which came out of this were rather rustic, so they were built from pieces of wood, whether they were sleepers or longitudinal sleepers, all sorts of things. And they were very often referred to as railways, railroads, tramroads, or tramways. They were not called railways in those days. Now, the word tramroad is interesting because it comes from the German word trammel. So a bit of the history of railways is in tramroads and tramways. And the German word means a trammel, a piece of wood. And so it's very descriptive. A tramway is something which runs on wood. Now, one of the big things which people discovered when they started building railways was that there's a fantastic transfer of a very great load to become a very small load once it gets into the ground. From a network rail standard here, we can see that the load on a wheel, the dynamic load, is 350 kilonewtons, which is equivalent to something like 35,000 bags of sugar. So that's quite a lot, really. And in terms of a load, what I'm showing here is the pressure distribution from the top of the rail down into the ground. And if we look at that logarithmic scale, then we should see here the railhead. At the railhead, you've got a load of 2.8 kilonewtons per square millimeter. Now, the contact between the wheel and the rail, as we probably know, is 100 square millimeters, or maybe 1 square centimeter. Now, 2.8 kilonewtons is 280 bags of sugar. Now, you have to just imagine 280 bags of sugar sitting on 1 square millimeter. That's just amazing. And the steel wheel and steel rail can cope with that. Now, as you distribute that load, first of all, on the over the foot of the rail, then the sleeper, the ballast, sub-ballast, etc., it sort of drops down to 0.35 Newton per square millimeter when you start to go onto the natural ground, which is why you can build railways across swamps, because that load is basically just about 35 grams per square millimeter. So that's everything can take that. Now, when it first started bringing the track and the train together, people thought it was never going to work, that the wheel would simply spin on the rail. So Trevithick, Burton, Blenkinsop, Eisenbach, Kingdom, Brunel, they were all convinced that steel wheels on steel rails would inevitably spinning. So, of course, Trevithick was the first man to actually build or have built a sensible locomotive. And what we can see here is a replica of the Penny Darrant locomotive. It had a little problem because it had only a single cylinder. So if you didn't get the sort of flywheel to operate correctly, the whole thing wouldn't work very much. And Trevithick wrote to one of his friends that the locomotive, the fire burns much better. And that was basically a very famous saying, because it happened when he put the blast from the cylinders into the smoke box and pushed out the smoke by that means, and actually pulled with that fresh air into the firebox. Now that was a huge achievement, and Trevithick did a very good job of this. One of my former doctoral students actually chose this as the title of his PhD thesis on improving the exhaust arrangements of steam locomotives in 2006. Amazing. Now, Trevithick did this experiment, and he then decided that he would actually get a lot of people interested by running a second locomotive, Catch Me Who Can, in a circus near Euston Square in London. And that was a very brave attempt, because the steel was not around yet, so the wheels of the locomotive managed to destroy the wrought iron or cast iron rails on a regular basis. The locomotive derailed. Now, there was a reason for this. Trevithick had actually serrated the wheels of his locomotive because he didn't believe in the power of adhesion, and that's why the rails were not lasting very long. Now, John Blenkinsop had a different idea. He created a rack alongside the rails, and we can see that in this illustration here. And on the locomotive, he had a pinion, and the pinion was driven from his two cylinders and pistons, and that's what propelled the locomotive. The wheels otherwise were just running freely on the running rails. Of course, this was a very good attempt, because it lasted about 10 years, and it was quite successful because you could also go up relatively steep hills where that was necessary. And of course, the rack and pinion system was then developed by Marsh, Rickenbach, Abt, and others. But I think the important point to note is that this was in 1812, when people today think railways didn't exist, but they did, very much so. William Burton built something called the steam horse. It was at the Butterley Iron Works in Derbyshire, and he didn't believe in adhesion at all. He had a very complicated mechanism which walked the locomotive forward. It managed to haul 2 or 3 wagons, and it managed to get up fairly steep gradients for the time. 1 in 36 or 3% is steep. And it was a success, but unfortunately somebody tied down the safety valve because he was blowing all the time, and it blew up the locomotive, and several people were killed. And so that was the end of William Burton's steam horse or propeller. Now, in 1812, things changed dramatically, because in 1811, Christopher Blackett, the owner of Wylam Colliery, had asked William Hedley, the colliery viewer, and Tim Hackworth to experiment with adhesion. So Hedley had a test carriage built, which we can see on this slide here, It was propelled by 4 people cranking, and what Hedley could show was that with the mass of the locomotive, which was enlarged with sort of buckets of some heavy substance, you could actually haul more than the locomotive weight itself, because that's what the original idea was. You could only haul with the weight of the locomotive itself. So a proper experiment, properly tested, scientifically carried out, and that's what then gave the second element to have successful railways. And adhesion works rather well, as we can see here. And the steepest gradients which I've come across with purely adhesion operated railways, Lisbon trams, the old ones, which work up to 1 in 8.33, and if it's a tight curve, they can get up to 1 in 7.4, which is not such a good idea if you can't brake. Now, William Hedley and Timothy were, of course, working in the area where most of the early railways were built, and that's the area of Newcastle upon Tyne. And if you look at the numbers on this slide here, it goes back into the 1600s, late 1600s, early 1700s, and this was a wagonway network. Now, Wylam Way is to the west, about 8 miles. Wylam is also Stephenson's birthplace, and that's where William Hedley built his first locomotives and had a very successful time there, shifting loads along the track. Initially, those locomotives had ordinary cart wheels and they were running on angle iron, but over time they were equipped with proper railway wheels. And so you can see a Puffing Billy built in 1815 by Timothy Hackworth and William Hedley. It was still in running order in 1862, and that picture which I'm showing here is from 1862, and it ran until the 1890s when it was transferred to the museum. It's now in the Science Museum in London, and is the oldest preserved locomotive. The second locomotive built was Wylam Dilly. That was a year later, and you can see there were some improvements compared to the original locomotive. And I mean, both of these are preserved, and that's the amazing thing about it. The Wylam Dilly is in the Science Museum in Edinburgh. George Stephenson, if you go back to this slide here, grew up in Wylam. His birthplace is a National Trust property, but it was closed to the public in 2017 because there were not enough people visiting it. And I find that a great shame. But George Stephenson built locomotives for Hetton Colliery, which is about 12 miles to the southeast. And this is one of the locomotives which he built in 1822. It's pictured in 1903, and it was in continuous use until 1912. Now, it was probably the story of the broom. There was not very much left of the original locomotive, but it's just a huge achievement. And it was managing to haul significantly long trains. It was complicated, but it was a great success. It traveled over 8 miles every day, lots and lots of times. Now, George and Robert Stephenson, of course, built the Liverpool and Manchester Railway Rocket, which was built for the competition for the Liverpool and Manchester Railway, which took place in October 1829. That locomotive is also in the Science Museum in London. And everybody talks about it because it's so spectacular in terms of speed. But the main criteria for the competition were reliability. So yes, you had to achieve 30 miles per hour, but the important thing was that you could achieve it for a whole day. And so on the third day of the competition, Rocket covered 112 kilometers or 70 miles. An absolutely fantastic achievement. And unfortunately, none of the other locomotives made it on that day. And to some extent, rocket is the reason why everybody believes that Stephenson created locomotion. But Stephenson basically just brought together two things. He brought together Trevithick's idea of putting the exhaust steam into the smoke box and the idea that you could have smooth wheels pulling trains, which he had from William Hedley. So the Northeast did an enormous amount for railways. Now, what I'm trying to say really is that Stephenson was a systems engineer. He brought two systems together and added the components which other people had invented before him. So he built a system, but he actually, if I want to be honest, I think he built a system of systems. We've got lots of different large-scale entities which together make something new. They make a railway, the track, the underground, the train, they make the railway. It's nothing on their own, although people did build road steam engines, but they did not have the same performance as a railway. The emergent properties are high efficiency and large haulage. Now, people tend to say that nature is a perfect system of systems, isn't it? Well, I don't totally agree. This shows a tree which grew on a big rock. And that was quite successful because it didn't have any competition at the beginning. But as it grew bigger and its leaves became more exposed, and the tree suddenly was pushed over by the wind, which was not its desire, but that's just what happened. We have another tree here, and this tree chose, or did it choose? It just grew out of a rock. And as it grew bigger and bigger, eventually it split the rock fell over, and the tree died. And what that sort of says to me is, once established, trees have no options. And nature actually allows things to go wrong because there is no control as such over it. Now, if people, humans, design a system of systems, that should not be the case. But I've got an example here where people have taken some potentially slightly wrong decisions. It's Crossrail in London, and I'm just showing one aspect, or two aspects, which is the depots and the signalling systems. Now, the depots are in strange places. It's where there's land was available. Normally, you would have the depots at the end of the line. So the first train in the morning starts to pick up commuters. So maybe not the best choice. And then, of course, having 4 different types of signaling systems was not an ideal solution. I'm saying 4 because the legacy systems on either side of the City of London are not exactly the same. So make the right choices, because as people we can do. And so often people say systems of systems are something which is 21st century. It's only become important since computers. But Rhiannon Evans and Duncan Kemp have looked at it in a bit more detail, and they said generic characteristics of systems are a level of independence, the rapid evolution of requirements, what you demand of the system, lots of stakeholders who have different views, and very little incentive to work together. And as you put all these things together, you get new behaviors which you potentially didn't expect. And systems of systems are often geographically dispersed and connected through a network. And Rhiannon looked at early GB railways, so that's 200 years ago, and what you saw was 150 railways with separate owners and operators. They rapidly grew the network with services, passengers and performance. People all had very different needs and aspirations. People wanted not to just travel on one line, they wanted to travel on the network, and that required new rules. And very quickly, this system of systems spread across the whole country. And really, railways are a classical example of a system of systems, and until the British Rail was created to bring them all together into one organization, they were very, very disparate and very difficult to look at. So when we actually look at the railway, they are both complicated and complex. They're not just one of the two things, and I'll explain the difference between these two terms in a moment. So if we look on this slide here, we've got, let me see whether I've got the cursor. No, I haven't got the cursor. We've got the dispersion of the system, the fact that it's a network. So we've got physical dispersion because the railway tracks go all over the country, and the organizational dispersion because we've got people working for the railway from Penzance all the way to Wick and Thurso. And that makes managing the system quite difficult. But it's not insuperable, because if you've got good databases, good rules, good regulations, and well-trained staff, it's handleable. You've also got lots of different types of subsystems, components, material types, asset performances. There again, physical diversity and organizational diversity. And organizational ones are about things like staff skills, stakeholder requirements, fare systems, etc. But again, this is complicated, but you can manage it with good rules, good regulations, and good databases. And computers help us an awful lot. Now, the blue things down here is variability. Now, variability is something which is complex, because it's not something which we can address with simple rules or databases. We can design the system to work, but we can't actually guarantee staff performance, what the stakeholders want. Third-party activity is a particular problem organizationally, because if you have a level crossing, you can't control what the car or lorry does. Most of the time they are well behaved, but not always. And you can't predict what Earth is going to do, what the ground is going to do, what the weather's going to do. The weather becomes worse, so that makes life more difficult. So complexity is a very important issue in railways. On the right-hand side, we can see another aspect. We can see the coupling between subsystems. So the wheel and the rail are very tightly coupled. The pantograph and the overhead line have to be designed for each other. So the same happens with switches and crossings and the trains. And on the organizational side, you've got very close coupling in the timetable, the rosters and schedules. If you haven't got the driver, then on a non-automatic railway, you don't have a service. And the roster and the timetable have to work together. And then you've got the interactions between the subsystems. And those are physical again and organizational. So you've got the track forces, the maintenance required, etc. And again, all these things are much more difficult to manage than something which is just rule-based. Something's not happening here. What I'm showing here is sort of an overview of these features: the dispersion of the railway, diversity, the variability, the coupling of the subsystems, and that becomes very important shortly, and the nature of the interactions. And so the facts at the top we have already looked at. The first two, dispersion and diversity, are complicated, and basically we manage them with computers and people. The variability is complex, and it's much more difficult to manage, so we have to plan it into the system when we build it. And then here, with couplings of subsystems, we have got what's called loose coupling and tight coupling. So if you have a car on the road or a plane in the air, that's not so difficult. But we have got tight coupling between the wheel and the rail, so really you need the two be to very good standards and tolerances, otherwise it doesn't work. And organizationally, if you have tight coupling, that means that you need the staff in the right place at the right time, for example. And then you've got the nature of the interactions between subsystems and behaviors. And a linear interaction is something where things just sequentially happen. If you have a piece of plain line rail, the trains can only follow each other. So that's quite linear. But where you have got junctions, you get enmeshed or complex behaviors. A restaurant kitchen where everything has to be ready at the same time, that's a complex system. And it's very difficult interactions. And then organizationally, you have got similar issues. The main one on the railway is that we operate and maintain the railway in the same place, and that presents risks, and it represents very difficult situations. This is called interdependence, according to a guy called McKechnie in Dublin. He's not written a lot, but it's like thinking on what makes systems difficult to manage. So I've already gone across that. Basically, complicated aspects of the railway can be managed by means of lists, databases, and procedures, and the right person in the right place. This is a typical asset management example for a railway, where we've got dispersion and diversity. On the railway network of Victoria in Australia, there are 2,200 point machines, and if you count, it's roughly about 30 different types and 30 different generations, and some of them in large populations, somebody in very small populations. And that has to be managed. But you can look at the list and you can see, yes, we can manage that with a database and the right people with the right skills, being in the right place at the right time. But that's manageable. In terms of complex aspects, well, I've talked about close coupling, I've talked about variability, and the big thing in railways is the interaction with systems that are not under the control of the railway itself. So that's level crossings, it's stations to some extent where people interact with the railways, and any activities where you've got people involved. And that's not the negative thing about people, but it's just a fact. Where you have human decision making, there are potential issues. And you can only manage all this during the design phase of the system and by good continued management afterwards. Now, this is an example of variability, where you've got operational targets for reliability here, which is all the services delivered, and the punctuality. And you can see that this is also from the state of Victoria. From March of this year, the reliability and punctuality rocketed up because there were no passengers. Now, we can say that's really terrible and it's not good for us at all, but it's a very good lesson. If we can manage our passengers better, then we have a better service. And if we have too many trains in a location, then things go wrong. So the Deansgate corridor in Manchester is a typical example of that. That at the moment is working extremely well because there are fewer trains and a lot fewer passengers. Now, Charles Perrow, who was a sociologist at Yale and Stanford universities in the States, he came up with this idea that systems which are closely coupled and which have got what I call enmeshed interactions, or he called them complex ones, but I don't think that's a very good word, have the potential for catastrophic failure. He says no matter how much money you invest, how much effort you invest, accidents and incidents are not avoidable in very complicated and complex systems, regardless of any effort you make. Technical solutions are not adequate because most incidents have some form of organizational roots when you actually look at the end. And we may have to abandon complex technologies, what he says, and keep things simpler if we want to have fewer normal accidents. Typical examples of these are the 3 Mile Island nuclear plant accident and also the Fukushima plant accident in Japan. There were lots of things to prevent the catastrophe, but all of those hurdles were overcome and the failure came through. And to me, Stonehaven is an example. It's not a clear example, but if you think about it, the infrastructure was designed based on historic weather, not climate crisis weather. There were 52 millimeters of rain in 4 hours, and that's the same as you would get in almost the whole of an average August. And what we can see on this slide here is a big field up here, then a field drain, and that field drain went down in a closed drain covered in gravel, and that drain then led into a trackside drain down here. Now, the huge amount of rain effectively washed out that gravel and deposited on the track, and that's what caused the horrendous derailment. Now, I don't think you can blame anybody for not having predicted this. Basically, too many things came together to create a situation where the system just couldn't cope. And so, to me, that's an example of a normal accident. This is the first accident where people died in a movement accident of the railway since 2007. So 13 years. And okay, people may have got a bit complacent, but I don't think that was the cause of this accident. Complex systems basically don't follow predictions. They respond to particular events in their context. They respond to component senses. They adapt to the environment. They adapt to other agents in the system, and they evolve. They specialize, they generalize. And the picture here shows a sort of the evolution of beings, plants, animals, and humans. And they all ended up very specialized, but you could not have predicted that. So Ryan Kitchens, who is a software engineer, basically said, when you work with systems like this, you really can't try to prevent failures because they are not predictable. You can't put in enough defenses to make it work. What you can do is you can learn when things have happened, and you can observe the system when it is going well and make sure that you know why it is going well rather than why it is not going well. Because if you think, the number of incidents we've got is very, very small. And so he has three themes here. He has comprehension. Incidents can't be fully understood. They are fraught with uncertainty, and any remediation which you put in, any mitigation, may actually contribute to future incidents. The drains at Stonehaven were put in 2010, and since then the weather has changed significantly. The second thing is understandability. Managing the small stuff does not prevent big incidents. They are not made up of causes. We don't find the causes, we construct them after the event. So with the derailment and fire at Llangennych, what we discovered later on was that brakes had been left on one of the wagons. A wheel overheated, or actually a wheel set overheated, and as a result, the train derailed and a fire was caused. Now, there were hot axle box detectors, but they are not asked to look at the wheel temperature. So yes, we now know what happened, but it was unpredictable. Which is the last point. Learning from the last incident will not allow you to predict or prevent the next one. Complex systems are not deterministics. We can't precisely or repeatedly foretell what's going to happen. And again, Ryan Kitchen says a lot of it is about the fact that success and failure have the same genesis. You're undertaking your normal work, but there is performance variability, both of the kit, but more importantly, of the people doing things. Now, that performance variability leads to people using workarounds or not complying with the rules. And very often, that is actually what leads to success. And an example which he gives, which I think is very good, is a helicopter not quite landing in a mountain in the snow, but landing enough for people to get on. As it does that, the helicopter blades go through the snow and create a cloud, and the helicopter takes off, and everything is perfect. Now, there was no compliance there were workarounds, but it led to success. Now, if there had been a stone or ice in that snow, the workaround, the non-compliance, would have led to failure, and there would have been an investigation. The pilot would have been accused of being reckless. Had he survived, he would have probably gone to prison for a number of years. But basically, what we need to realize is that the same routes can lead to success and failure. So we need to try and learn how they get to success and try to understand what are the criteria which makes them successful. So just to constrain variability does not actually work. So Kitchen suggests a major approach, and it differs in some ways from Toyota. Toyota always said, when you have an incident, you ask the question, why? And when somebody tells you why, then you ask a question, and why did this particular situation occur? And Kitchens actually says something very simple. Don't ask why. Ask people how. Because if you ask people how, they will tell you a story, what their experience was when things were going on. They will not come up with a theory why things went wrong, because there are no root causes. It's all lots of things coming together. So allow a person to tell you what they thought at the time, what they saw, rather than why they thought something was happening. The how is very, very important. And when you've got an incident, don't call it a catastrophe. Call it a surprise and try to learn from it. And I've already talked about the Deansgate corridor and what you can learn from the COVID experience. Now, we teach all our students that when they design a system, they should use a systematic approach. And what we usually use with them is the CENELEC system life cycle, but there's lots of other V models of a similar nature. It starts with having a concept, an idea of what you want to achieve, what you want to do. And that's usually from a stakeholder or lots of stakeholders. Then you've got to go into some detail and find out what this actually means, what the requirements are, which bits of the system does what. Then you design and implement it, you make it, you install it, you validate and make sure that it actually does what you want it to do. You take it into service, and then you accept it for service, you operate and maintain it, and at some point you decommission it. And there's lots and lots of verification stages as you go down here. Make sure that it's actually built what you want it to build, and here that it actually does what you want it to do. Alex McGrath and I were talking about this in a talk at an IRSE seminar. Now, in this area here, we understand the problem. That's so important. The concept itself is not understanding the problem. It's just an idea. In this area here, we implement the system. And that's a very important phase. And it's not the same process as the understanding of the problem. And then we operate it and maintain it. And so these are the main phases. Now, when we look at that in a bit more detail, this is about dealing with complications, because we have got spreadsheets, we have got Gantt charts, etc., to deal with all these things, and we can put a database in, and that works quite well. Now, addressing complexity happens at the beginning. When the concept is brought to us, we have to say, yes, this might work, or no, this is far too complex to work. The system definition, we need to ask which complex aspects could affect us, and when we do the requirements, we need to say, in order to address this particular complex element, this is what we have to do. And when you actually run the system here in real life, There's lots and lots of people involved. There's lots of external variability involved. And so we really need to deal with complexity at that point. Now, Alex came across resilience thinking by Brian Walker and David Salt, and she's used some of that in order to think about how things work. And effectively, we start with reorganization. That can be a new system, or it can be a system which we are changing. And it's very much about experimentation. We're trying to find new and novel ways to do things and creative ways. The next phase, as we sort of start to implement this system, we were starting probably to invest a lot of money. So when the railways were first built, as I showed, we had some experimentation for probably about 30 years. And from 1830, there was a huge explosion in investment. And lots of people built lots of different things. And then people started to standardize. They agreed that the standard gauge was quite a good idea. They agreed lots of rules which were common. And that's where you conserve your system. And then at some point, a shock comes about, an internal or external shock, and the system has to change. And we are starting to reorganize again. Now, at that point, we will probably start to do a lot of problem solving, but it's complicated. It's rule-based again. And what happens on the system release side is about resilience, and that's about dealing with complex behaviors. And so we set up the problems right at the beginning over here, but the problems really only come about when we have got the shock to the system. And we then have a crisis which allows us to start again. So at the moment, Network Rail is looking at all its embankments and all its cuttings in order to understand what is changing. And so when we go from resilience to making things work, we have to really go from this side of the loop to this side with our lessons. There's two examples here of slow-moving systems which ended up in a crisis. So Hatfield, the derailment accident, over many years, the tracks had deteriorated, but they deteriorated very heavily on that particular line because of lots of trains using the track at the same speed and with the same type of trains. And it was a very close coupled system. The gauge corner cracking occurred. There were lots of organizations involved. The rail wasn't replaced on time. The faults were not effectively reported because they were actually reported. And access to the track was not regulated properly. So a lot of communications issues because people had not thought ahead of what actually might be needed. And it led to complete disaster. Now, last summer, summer 2020, Kiwi Rail observed that its rails were decaying much more quickly than expected. And they did a lot of testing, and then they started a resurfacing project very quickly and replacing the routes. 100 kilometers of track had to be replaced and the railway was slowed down. But in the end, it was a successful management of what we call system-wide stress. So rather than system-wide crisis, you can actually deal with that. That was it, really. That was my sort of theory introduction. And I'm now going to talk a little bit about the history of me and my brother, because we have always been very close, and particularly in our love or interest for the railway. Our dad took us on train journeys, and here we are on a train near Zurich, Thomas and on the left and me on the right. And Thomas was probably even more interested in railways than me, and when he started to paint pottery, trains had to feature. And of course, they were steam trains, they were freight trains, they were passenger trains, and of course, even electric trains, because in Switzerland, 98% of the network are electrified. If it's not 99, I can't remember exactly. We had a model railway. Thomas built a lot of things for the model railway, and it had an influence on both of us. I went to school in Zurich, in Switzerland. I did a baccalaureate with Latin and Greek, which people thought was a bit peculiar when I started to study engineering. But I was interested in maths, and I wanted to learn something about maths, applied maths. And Thomas had long before me decided to do electrical engineering. And really, when I decided, he was very disgruntled because I started before him. So these things happen. I did an equivalent of an MEng in electrical and electronic engineering, but really that was just theory. I didn't understand electricity at all. I then did a postgraduate diploma in third world development, and after 2 years as a software engineer, I decided that life was too short in order to spend it on designing software code. And I applied for a job with GC Traction in Manchester. And there I learned about electricity as a practical tool, as something which you can use. And it was so good. I then became a research assistant in very low current electronics, so microamps instead of thousands of amps at UMIST. Then that was only a year. Then a research associate in mechanical engineering at Salford, a lecturer in computer integrated manufacturing at Brunel, and then I did a PhD in engineering education. But let's go back to my time with GEC. I was working quite a lot of the time at the Vulcan Foundry in Newton-le-Willows, which is between Manchester and Liverpool. And that factory was open for 170 years, from 1832 to 2002. And it built locomotives for all over the world. It is now, unfortunately, a housing estate. But this picture is quite important to me because it shows what's called a man rider, which was used at Easington Colliery. So that's very close to where Hetton Colliery was. It went right under the sea, and it took the miners to the coal front, which was several miles out underwater. And this is the team who was building the locomotive, or rather rebuilding it. And we've got a very important person here, Paddy. And Paddy was a foreman at the factory, and he had lost part of his leg during a works accident in Nigeria when he was working for the company. Paddy had a very, very great ingrained hatred of managers. He really couldn't stand them. And any manager who came into the factory and wanted to say something was greeted with the F word every second word. Now, I was young, I was 28, and I could not believe this. So I just didn't say anything. I went home and I practiced my swearing. And the next day I was in Vulcan. I said to Paddy a very, very long stream of very nasty swear words. Paddy was shocked. He looked at me and said, "Why are you doing this to me?" I said, "Well, I don't like what you're doing to me. Can't we just be friends and forget about all this?" And he said, "That's probably quite a good idea." So we were best friends from that, and it made my life so much better at Vulcan Foundry. Now, it's not a traditional approach to man management, but I think it worked quite well on that particular occasion. By the way, Daniel Gooch, who built locomotives for Brunel, spent a few months in Newton-le-Willows, and he hated it. I loved it. And this is what we built at the time. I was involved in this IMechE locomotive, and you can see the young Felix in the background here, and the team who were building the locomotive. A fantastic team. They were really, really high-performing staff. Now, on the right-hand side, you see one of the choppers. It was the SEPEX, the second series of SEPEX chopper, so for separately excited DC machines. And what this gave me was a lesson in evolution and revolution. When I was working for GEC, we were making resistance control. We were building series choppers with thyristors, and I was involved in this first project of a SEPEX chopper with thyristors. Very complex technology. I blew up quite a few of those thyristors, each of them being about 2 months' salary of mine. Luckily, I didn't have to pay. Then we had series choppers and SEPEX choppers with gate turn-off thyristors. Then we had inverters with thyristors, inverters with GTOs, and now inverters with IGBTs. And so about 8 different technologies, radically different technologies in 40 years. And where are we going next? What is the next technology which might be useful? Well, we already know one of them is a new type of semiconductor material which makes things more efficient. Now, the Rolls-Royce has been building the Trent engine for 50 plus years. Yes, it evolved a lot, but if you look at it, it's still recognizably a Trent engine. And that means they have lots of learning from history, whereas railways find that much more difficult. If you just look at these examples, that's why we might have difficulties building new things. But one thing I knew, I would never be a teacher. I was absolutely certain of that. Our dad was a teacher. He was also a journalist. Mum very much believed in education. She was a very competent lady, and she was very determined on our behalf. So she managed to get us some private maths tuition for struggling kids. It was a very good earner. And unfortunately, it started to influence me to think that teaching was not so bad. While I was at GEC, I taught literacy and arithmetic with the National Association for Care and Rehabilitation of Offenders. And while I was at Salford, I was introduced to teaching in the classroom. My supervisor said, "You just use the Kalashnikov approach." I said, "I can't shoot students." He said, "No, you don't, but you come as close as you can." So what you do is, in the first lecture, you identify which students cause problems because they're chatting all the time. And in the second lecture, you ask a really stupid question and pick out one of those students. And everybody knows why you picked them out, and then you have peace. So it was probably how I slithered into teaching. And as so often, it was Seri's fault. Serendipity is at my side when it's a question of changing jobs. So after Salford and UMIST, I got the job at Brunel University, and it's a slightly older young Felix here. I was told to teach computer integrated manufacturing, and I said to Ray Wild, my boss, "I don't know what this is." And he said, "Well, neither do I. You just have to teach it." So I thought, well, actually, why don't we learn together about what it is? So I set up a team exercise where a group of 30 or 40 students were building a computer integrated manufacturing system. And that sort of led me to thinking systems are interesting. And what they did, they learned about leadership, they learned about management, and they learned about technology all at the same time. And I could write a PhD about it, which was quite useful. Now, when I was working for Brunel, they changed quite a lot of things. I was not very happy. And at that point, Thomas said, "Felix, I was offered a job as a railway inspector, but I don't want it because they want to put me into cable cars." So I said, He said, "Why don't you go and talk to them?" So I did. And they said, "Oh, I think you know quite a lot. And you can talk several languages and you can speak to anybody. So why don't you join us?" So I did. It wasn't a huge success. I was not really suited to being a civil servant, but I learned a lot, and I could test a level crossing, which was in this countryside. Behind here, you can see the Morteratsch Glacier, and it's probably the nicest level crossing in the world, or at least in my view. After that year in Switzerland, I managed to get the job at the University of Sheffield, and then I became a professor at Birmingham. Now, during the time with the Swiss Inspectorate, I came across a very sorry tale of a poor systems engineering approach. You can see here a mountain railway in the Swiss Alps, and you can see it's a very difficult terrain. Lots of tunnels, narrow ledges and cuttings, and it was built for conventional trains, but Switzerland had taken on responsibility for hauling roll-on, roll-off trains across this mountain pass. And it was the railway had to come up with a solution of doing this, which was a solution that was going to be redundant when the base tunnel was built. So what they did, they adapted as much route as they could to accommodate these 4-meter high trailers. In many places, they couldn't do it on both tracks. They could only do it on one track. And the existing track, which was still there, could only accommodate passenger trains. The interlockings didn't recognize these different trains. The ATP system couldn't recognize it. The pocket wagons couldn't be modified. So basically, there was a very difficult situation. And the biggest problem was that they didn't expect the drivers to be able to learn enough about the route to make the right decisions at all times. Route setting errors would occur, and there had to be a way of preventing accidents when that was the case. So they came up with something called the violet signal, and that was seen as an out-of-gauge interdiction. So wherever you had space to build both tracks to the right size, you did. Where you couldn't, then you had a signal with a violet aspect which indicated that a out-of-gauge train could not go through there. So you set up your system, the train describer, to set the correct route, and if there was a problem, the driver would see the violet signal and would stop if they were in charge of a large train, not if they were in charge of a passenger train. And that was installed, and the railway then came to me and said, is that fine? Can you sign it off? And I said, no, I can't, because it's not safe. They said, oh, it's a 2-channel safety principle. It works. Now, a 2-channel safety system, as I tell my students, requires 2 completely independent channels. They don't need to be fail-safe each in their own. But when you combine them together, the probability of failure becomes very, very small. So here I gave an example with the reliability of the human, about 0.002 mistakes per 1 entity, and a lot fewer for the technology system. So in Britain, we have TPWS, and that's exactly a system like that. TPWS does not know what the driver does, and the driver does not know what TPWS does. And so with that sort of probability, if you have an incident on 10 locations per journey, that gives you 1 wrong outcome in 5 million journeys, where the TPWS and the driver fail at the same time in a dangerous situation. So in this particular case, I said to the railway, it's not a true 2-channel safety principle, because the driver has to make a decision which is based on the situation. So the driver only has to stop if they see a violet signal and if they're at the controls of a locomotive hauling an out-of-gauge trains. So it is no longer an independent situation. The driver has to do something which is related to the situation where the automatic system is working. And here is just an example of how this is set up with the conventional Swiss signaling system with the violet aspect at the bottom. So the application is an example here. It's not from anywhere on the route, but it's just an example. You've got a track which goes, or 2 tracks which go through tunnels. The track which is in dotted lines is not accessible for heavy haul trains, and that means that you have potential for risky situations wherever you move from an out of gauge train compatible track to one which isn't. So in this case here we've got 5 situations where a train could do the wrong thing. And so you erect lots of signals which have either no interdiction aspect or they have it, and you can see quite a lot of the signals have got an eye, which means a violet aspect. And I said to the railway, well, what you're doing, you train your drivers while they're driving passenger trains or standard freight trains to ignore that violet signal, and it may take years before they come to a situation where they're actually seeing the wrong situation, where the violet signal actually means something. And they did a calculation. If you were running mixed passenger and freight services, then you would 17 times on a passenger trains in a 3-hour shift, you would pass one of these violet signals, and you had to pass it. And I also calculated that after about 15 years, you might actually be at the controls of a train which had to stop. Now, can you imagine the likelihood that the driver would actually do that correctly once in 15 years? Very, very unlikely. And I thought this was not going to happen. But this is a recent picture of the violet signal in action. And so the trains which go over the top when the base tunnel is closed still have to observe the violet signal. Far fewer situations, but it's still a risk. Now, the Swiss train driver is a very good train driver, so I'm quite confident that he will not have a problem. Now, at the end of my year in the Swiss government, my friend Serendipity said, there's a talk about his PhD by a guy called Marcus Monteagle, who has since become a friend, and it looks interesting. So I said, oh yes, Seri, I'll go and do that, and I'll not go to the job interview in Cambridge, which happened to be a very good decision, because very shortly afterwards I went to see the University of Sheffield about joint research, and Andrew Jablonski offered me a job, which was funded by British Rail, to set up a master's program to do with railways. Bill Steinmetz, Colin Goodman, Robin Hirsch, Roger Goodall and Rod Smith all supported me in setting up this program in railway systems engineering. The rest is what we call history. Well, we did learn a lot of things while we were doing this. In 2010, I had 13 Turkish students on the MSc. We thought there's too many people from the same background. There's too many novices to the railway. We need to do something. So we created what has become known as the Working Weekend in Wirksworth to develop team spirit and enthusiasm. Bridget and I tend to cook breakfast, which is how porridge becomes a tool for educational enhancement. And this is a typical set of pictures from our Wirksworth experience. The Turkish group at the top, and a more recent group at the bottom, and then Bridget and Felix cooking, and everybody eating the meal which is prepared by somebody from the railway. You can see people seem to enjoy themselves. It's very hard work. You need good committed trainers and educators, and in this case I had Mrs. Stakhanov on the team as an instructor, and hopefully she will actually do something if I get... Oh, she does, yes. And that's how a student learns from an experienced person. And Göran is now doing a PhD. She is in that short weekend. she turned from a totally inexperienced person to somebody who was confident in handling complicated tools in heavy load situations. And we did things like carrying rails in groups of 20. We observed what other people were doing, and that's what hopefully is going to happen again next year after, or well, resolved some of the COVID issues. The other thing we did was to create study groups, study tours, because we realized that students needed to see different technologies in different countries. So here we are visiting the Chemin de Fer de Provence near Nizza. And this is Thomas, my brother, a bit older, and helping leading study tours, and Charles Watson, who is one of my colleagues, who is my boss on study tours. We've done about 30 with the railway groups, lots of different things seen. Sadly, we can no longer go and visit Maglev. And a bit more of systems thinking came about when SMRT, one of the operators in Singapore, realized that they were no longer managing a new red metro. Both the kit and the people required upgrading, because the kit was 30 years old and the people were retiring. So they had to get new people, and we have been teaching there since 2016. And here we can see the group of people who do this: Clive Roberts, my boss, or former boss since I'm retired, Pietro Triccoli, Hong Shin Kim, Holly Foss, who is my successor, Bridget is somewhere here, and Felix, Clive Cashin, and Zena, and a team of up to 200 students learning in different groups. It's fantastic, but it's very hard work. It's not a holiday in Singapore. Now, people found out that I was running study tours, so I was hired to run study tours for the IMechE. Here, a visit to the Bochumer Verein, who make wheel sets. And, of course, we also visit museums. And here, Felix has to take a picture of a track brake, which, of course, is very common on trams. And on the right-hand side, he's a guinea pig, because you've got the little problem of not very much space between freight trains moving at 40 kilometers per hour and railings to go down the stairs. It worked. I'm still here. I support the charity, which is the Railway Children. It's my favorite charity. The picture on the left is when we did the Three Peaks Challenge. I'm hoping to do that again next year. And in January, I tend to take part in the Railway Children Sleep Out. And I will probably ask you all to support the Railway Children so that I can be top fundraiser again. Now, it's time for the thanks. Lots of photographers have helped me. The students and teachers have actually made my career possible. People have provided ideas for this talk. People have helped me with the MSc development. And the most notable ones are Sharon, Holly, Francesca, Joy, and Deborah, who keep the students happy and who make the thing work, because academics are not so good at making things work. And then, of course, Brian Redfern, who was my mentor when I started this project of becoming a railway person. Okay, final things is a couple of announcements. The Automated Railway Seminar has been and nearly completed, but it is still available online. So both the lectures by 20 people and the 2 live webinars are now online and have become a real bargain. IMechE members pay just 65 quid for a full conference available online for the next 6 months. So I can strongly recommend that. The other thing which happened is that the annual luncheon of the Railway Division cannot be a physical event in spring 2021 because it's too risky to hire a venue for 1,000 people and take them all together. So we're going to have a VAL, which is a virtual annual luncheon. It's the same time on the same date, about 11:30 to 3 on the Friday, the 5th of March. There will be lots of networking, connecting. There will be tables, sponsor tables for 10 people. There will be an IMechE Railway Division. There will be a stimulating guest speaker. We'll be able to link businesses and chat. Hopefully people will dress up, even though it's a virtual event. Wherever people are, they can take part. We've already got bookings from Ireland and Australia. Invite your colleagues and clients and stand by to fix your own food. We will provide the recipes. And hopefully we'll make a decent surplus for 2 charities, and hopefully this will be the biggest and most international Railway Division annual luncheon. And this is the cost. If you want to rent the table for 10 people, which is basically a breakout room, it costs £150 instead of £1,100. Individuals pay just £18, and we try to have them in nice groups of 10s with a host from the institution. If you feel you want to do more, you can sponsor virtual programs, virtual bars, you can sponsor a physical program, you can sponsor activities, or you can sponsor young members. We have been practicing the menu. This is Bridget Eickhoff, who occasionally is my wife, and she is experimenting with the polenta dish, which is part of the vegan annual luncheon, but we've also got a meat eating annual luncheon menu. Thank you for listening, and I shall now unshare this presentation, and hopefully there might be 1 or 2 questions.
Thank you very much, Felix. Interesting and challenging at the same moment as ever. So we're now on to our Q&A session. For everybody who's unfamiliar with WebEx, there's 2 little buttons on the bottom right-hand corner of your screen. One is marked Participants, and the other one is marked Chat. If you click once on the one marked Chat with a speech bubble by it, you should be able to access the chat box where it says Enter Chat Message here. You can type your question in as you would do in an email or a text or whatever kind of device you use. So, floor is open for questions. Make sure you get your question in, because the only dumb question is the one you don't ask, remember? First one comes from Richard McLean. So, the standard UK railway approach to a crisis is to centralise command and control. Does railway history and the theory of complex and complicated systems indicate that such dictatorships help us extract ourselves successfully from the crisis?
Thank you, Richard. I am very strongly of the view that centralizing things loses local knowledge, and local knowledge is what allows us to deal with complex situations. We can deal with huge numbers of assets dispersed across the country using a centralized system, but dealing with complexity is much more difficult. We can set up the system correctly, but we do need local knowledge. If you think about it, the railway in Penzance is to the same standard as the railway in Wiek, but isn't the weather just a little bit different? Isn't the ground not a little bit different? So it's sensible to have common systems, but don't try to force it.
Okay. Thanks, Felix. So next one from Samuel Seabrook. Do you think the introduction of more battery electric trains will decouple some of the interlinked dependencies in the butterfly model?
Yes, battery trains don't necessarily need an overhead line for at least part of the route, or they are just recharged at the end of relatively short journeys. But we should be under no illusions about battery and hydrogen powered trains. With the best will, they will not have the power for high speed or for heavy haul loads. They are fantastic for relatively short runs and frequent starting and stopping in the case of batteries. In the case of hydrogen, unless we also have batteries on the train, we lose the energy during braking. So hydrogen is a good tool for carrying energy with you, but it's not necessarily that good a tool for running a train. So yes, hydrogen battery will make things simpler in terms of electrification, but as the recent analysis and network has shown, that's only a few hundred kilometers of railway in the country with low density services and relatively low speeds.
Okay, thank you, Samuel. Next one from Les Bryant. From a railway systems perspective, what are the main differences between the Swiss and the UK's railways that make the Swiss system so much more efficient and reliable?
I think reliable is true in Switzerland a lot of the time, but when things go pear-shaped, don't they go really pear-shaped? So, for example, we had a problem with a high voltage transmission line, which went wrong, and that stopped the railway working for several hours. But in general, yes, the reliability is high. It's partly because the resources are much more generous. So you have spare trains, you have spare tracks in stations. You can hold a train in a station if it's running very late or if it's running early and let another train go past. That's a resource question. But the other side of that is the efficiency. Apart from the intercity network in Switzerland, the railway is very heavily subsidized by the state. And very heavily, I mean 50% of the fare is covered by the regional authorities or the national authorities. So yes, the intercity trains are efficient, but the others are reliable and essential, and they only pay their way if you take into account the socio-economic benefits, not the financial situation. So does that make sense? So it's having extra resource, spending enough money on maintenance, and having a virtually all electric railway, because that's also something which makes things more efficient and more reliable.
Yeah, that makes sense. Perfect sense, Felix. Okay, we're getting some good questions coming in, so keep them coming.
You had one by Sam Marchant?
I do, yes, and I'm just trying to find it because the list has been scrolling up.
Well, I've read it, and so Sam, I think it's too early to say whether the new approach, which is not actually that new, is going to work. But essentially, we still have operators, but instead of having to beg for a little bit of extra money in order to get the profit, there's a defined profit, and that, or rather a defined rate for the job. And so we have some of the benefits of the franchise system without some of the drawbacks, but it really depends on how the system is managed. The problem will not be the arrangements, but the management of the arrangement, and I'm not saying any more.
It's probably wise. Okay, I've got two similar questions here, which I will combine, one from Roger Townend and one from Daniel Pike. And they're around the complexity of the technologies. So perhaps we're getting to a situation where we're now getting too clever. So which aspects of modern UK railway development might fall into this too clever category? And should we be minimising human involvement in decisions, or are we trying to catch the faults as they occur?
Well, as we were explaining at the Automated Railways seminar, there are things where automation is extremely helpful, but automation is generally designed by people, and eventually people will break it. That's one of the aspects. So automation in the right place is a good idea. Automation in other areas is maybe not ideal, particularly where you deal with the public. Automation may not be the final solution. The second thing is making things more complicated is okay as long as it delivers something, because you can manage it. Making things more complex with introducing more unpredictability into the system, that is very dodgy. So if you take Crossrail, the introduction of several changes between signaling systems, that is introducing complexity and risk of failure. It may achieve better performance in the core, it may achieve better performance elsewhere, but the performance of the whole system is the combination of all these things and the interactions, and that may not work so well.
Okay, I think there's one here that follows.
So I think there was a very good question when I gave this talk in India, well, virtually in India, and that was, should we change technologies quickly when something new comes about? And I said, well, railways are long-lived. If we have something which is not quite up to scratch but works well, let's keep it until it wears out, unless we have huge benefits from an improvement. Because we can't change all the point machines every year, just because somebody comes up with a better one. We have to make sure that we only change the things where it's beneficial. Yeah, sorry.
Yeah, that I wholeheartedly agree, Felix. So leading on to that, or leading on from that, I should say, risk assessments, I think this is from David, but no surname. Risk assessments by their very nature are required to anticipate every potential hazard which may affect an activity or system, and then come up with preventative actions. With complex systems, can this be achieved?
No, it can't. It can't even with complicated systems. It can't be with any system. Because if we try to learn from failures from the past, we have so many failures, and we can say, yes, we're going to avoid all those. But if you remember Reason's model with the Swiss cheese, where you have got lots and lots of defenses, and in each of them there are some holes, and if one of those holes goes all the way through, you have your accident. But when you're starting, you don't know where those holes are, and your best risk assessment will not be able to identify that. It's a fallacy to think that you can build a perfect risk assessment. You shouldn't try. You should try and find out why the system works well, and then draw the lessons from that and make your system continue to do that.
So that rather calls into question what's in the common safety method then?
It doesn't, I don't think.
No, you don't think it's incompatible?
No, there's no contradiction. You do need to think about the things which you do find out, know, and the things which you can do something about. But while you do that, you want to learn from where things go well. Because that will tell you something about what you need to watch.
That's fair advice. Felix, I'm going to take Chairman's prerogative for a moment. And I've got a choice of two questions, and I think one we've already partially covered, so I'll skip to the other one. At the seminar on automation, one of the conclusions seems to be that whenever we're designing a railway, we should include a degree of variability in how it's operated for, at the very least, better wear and tear characteristics of the infrastructure and the trains. The Hatfield accident you commented on suggested that too little variability in train operation was a factor. So how much variability should we try to introduce? What is too much and what is too little?
I think I would be very rich if I could answer that question easily. I think it's you have to understand what your performance requirement is, and if within that performance, you could take, for example, platform train interface and step heights. If your allowed variability is 5 centimeters and the system works well with 5 centimeters, then why not arrange things to vary within that range? Because that's not going to affect anything. Why try to make a step height of 0.5 millimeter and try and build a system which does that? You can't do it, so you might as well not try. So have a step height which is sensible and where the passenger actually sees that they need to lift their foot, is my example for that.
Mm-hmm.
And in the case of the violet signal, what I really objected there was that the opportunity for doing something different for a train driver only occurred every 14 to 15 years. Now, that just does not work. You need to be, if you were working with people, they need to be able to relearn on a regular basis. And it's not so good to just do that in very staged scenarios in a simulator.
I agree completely. I think if I was to try and do something that involved learning and remembering what the right thing to do once every 15 years was, I don't think I'd even contemplate it.
I wouldn't deploy you as a driver anyway.
Oh, well, I'm not the right characteristic. I know that. I have a very low boredom threshold. I couldn't do it. I'm glad that there are people that can, but certainly don't ask me to do it. Okay, so we've got time for one last question, if people can get that popped in very, very quickly. And if that's not the case, I will ask, here we go. What advice would you give DFT as they review Network Rail's recently published traction decarbonisation strategy? And that's coming from Rob Warnes.
I would say accept it, but, and there is a but, make sure that you don't end up with having a national decision process which does not take into account local issues. So if you take the East Coast Main Line, which was built partly over a swamp, and that was a big problem in terms of electrification, and the choice of system was certainly wrong for that. If you look at the electrification between Manchester and Liverpool, as I pointed out to my audience yesterday, there were some very innovative ideas which only came about because people understood Chat Moss, which is another swamp, and it's a very difficult swamp. So yes, the national decision taking is good. The DFT should understand that the people on the ground may actually know more than somebody in London or, if displaced, in York.
I think that's a very good answer, Felix.
Thank you.
In which case, I will draw things to a close. Richard, if you're there.
I'm here.
Could you do a vote of thanks, please?
Yes, indeed. It's my pleasure to give Felix his vote of thanks tonight. 15 years ago, I was fortunate in having the best job in the world, that of being chief engineer at the National Railway Museum. And I was invited by this stranger called Professor Felix Schmid to come and talk at the University of Birmingham at their end-of-year dinner party for the students. They'd all enjoyed a year of tuition on Felix's course, learning about railway systems engineering. My job was to entertain these students that had been on that course with an entertaining talk and to run a practical task for everyone at the dinner. I chose building a Warren Truss bridge out of rolled up paper, A4 paper, and each table competed for a bottle of champagne. And it was chaotic from start to finish, but I came to get to know Felix and respect and like him enormously. I was absolutely delighted when he was made Railway Division Chairman, and so tonight is my opportunity to thank Felix profusely for trusting me to entertain his troops and for coming here to entertain us tonight. Thank you, Felix.
Thank you very much, Richard. It's very heartfelt, and I certainly felt that inviting you to the after dinner speaker for the systems engineering module was exactly the right person. You do systems and you can tell people about it. And of course, we both share a lot of respect for the ancient engineers. And
yes.
I hope you didn't mind that I took Stevenson down a little bit.
That's fine. Thank you.
Jolly good. Thank you, Richard. Thank you very much, Felix.
Thank you.
So just a brief reminder, if you would like to come along to the Zoom after party, if you scroll up in the chat box, you should see the link. It should be highlighted in nice blue, bright blue text with the underline. Just click on that and it should take you directly to the Zoom meeting, which is now open. You may have to wait a moment or two for me to let you in, but Felix and various others will be there to have a chat with and raise informally the questions that you always wanted to raise but didn't want to type in, and we'll carry on for as long as that is useful and as long as we all stay awake. So thank you very much. We will see as many of you, I hope, as possible on the 17th of November, and do look for the remaining programme on near you. Good night, everybody.
Thank you.